Hey, how you doing? My name is Andrew Cole. This is my project 3 on roller coaster launch systems. So a little bit of background information. A roller coaster launch system is used to launch a roller coaster train at some specified velocity to fit the theme of an attraction or the level of thrill of an attraction. To integrate a system like this into a roller coaster, you definitely need a series of sensors, but mainly accelerometers and optical sensors. An accelerometer can be used to determine the motion, the quality of motion of any of the individual trains, and optical sensors are useful to determine where train positions are on the track. If you're having multiple trains on the track at once, it's useful to know where they are so you can help ensure some safety. And then hardware and software integration. So again, one of the main things with roller coasters in general is safety concerns. These are funneling an enormous amount of people in and out every day. So for the hardware side, you definitely want to make sure that all of your systems are in working order. You want to make sure that none of your materials are near or close to failure and everything's running smoothly. So a big part of this is redundancy. So on the software side, you want to make sure that your control systems can handle the wide variety of loads that they're going to be facing, whether it comes to um, different distributions of mass, different amounts of mass on each of the individual trains, just making sure a variety of these factors can be handled by your control system. And the same goes for the sensors, specifically with the optical ones. You want to make sure that every time a train does pass through an optical sensor, that the sensor is reacting to that. That way you can communicate with the other sensors to let them know what's going on behind and ahead of them. Again, redundancy on that safety. And for these, I would use a PID system for all the individual trains of sensors, if you will. They're very good at handling a variety of different inputs to give the good, consistent output. And that'll be part of a larger PLC network so that the sensors can communicate with each other, again, for those redundancy reasons. For modeling of the system, the mass of the cart was placed over here in the launch bay. There's a driving force, and this came from a drivetrain below the actual train itself. This would react as one sudden force. It was going and driving the train forward. And going in the opposite direction was the force of friction between the wheels, and I said steel for the material of the track. So using this, I was able to derive an equation of motion for the train. And using that, I was able to derive a state space model to represent the system. Using that state space model, I was able to derive a transfer function, which was later used when modeling the system in Simulink. And tuning methods. So one of the better tuning methods for a PID is the heuristic approach. You can see this a lot with the Ziegler-Nichols method and the Cohen-Kuhn method. I would personally use the Ziegler-Nichols method. It's much more simple to understand, and it's very easy to fine tune once you get a rough idea of where your values are going. So the way that I approached tuning for this one was to start out with the Ziegler-Nichols method. And once I got something that I was happy with, I was able to do manual tuning from there. Um, so when you're tuning something like this, there's a lot of nonlinear concerns that can happen, mainly drag on the vehicle, the different shapes of people, depending on who is sitting in the front, who is sitting in the back, shape of the car, it can shift no matter from cycle to cycle rather. And along with that, the distribution of mass within a cart is going to be different for every cycle. So making sure the PIDs are tuned to handle these loads is very, very important. So right here, I have my final system model that was made in Simulink. I have a constant of 25 because I was trying to get to 25 meters per second. This goes into a sum block through the PID, through the transfer function, and this is a closed loop function. So the response of the transfer function is getting fed back into the system to get to the output we want. And down here, I just have a simple derivative block going into a product block. This is going to take the velocity, turn it into an acceleration, and convert it into G's so we can see what G-force the passengers in the train are feeling. So modeling results. So one of the main goals of this modeling was to get the cart to 25 meters per second in velocity in a time of about 2.8 seconds. So I verified the system using two different masses. I looked up the average mass of a roller coaster cart, which is about 735 kilograms. And I also modeled it using 850 kilograms. In both times, I was able to get the results in about 2.8 seconds. And with 735 kilograms, the velocity was 25.07. And with 850, it was about 25.12. So very consistent across the PID and very little steady state error when going across both models. I also needed to model the acceleration in G's that the passengers would be feeling, and it was just under 6. So one thing that my model didn't take into account was the ramping up of the train. So from my model, it seemed as just an impulse. It was going at 25 meters per second suddenly, or rather, it was working up to 25 meters per second in an instant before dropping off. But as you can see here, it peaks just below 6 Gs of force. And system development. So when doing a system like this, safety is the number one concern. Again, for the volume of people that this is going to be catering to. So to ensure this, all parts of the system need to be regularly maintained. This includes all the hardware components, but as well as the software to make sure that the PIDs are running smoothly. All of the materials making up the track are not under any failure of any sort. And a lot of that comes with ensuring that the system can perform consistently within its specifications. And one of the worries with automation is just ensuring that the system can handle the load required of it. When automating a system, especially one like this, it's going to be dealing with a lot of people. And again, with that safety, we need to make sure that the computer at all times can handle what is being given. Here are my references. Thank you.